All right. So hello, my name is Corey Johnston, and I chose to do my presentation over the photoelectric effect, which is a subtopic of quantum physics. And honestly, when I was choosing a topic, I thought quantum physics would cover things about, I don't know, that explain Ant-Man superpowers or something, or maybe like theoretical time travel, but it wasn't even really close to that, and especially not the photoelectric effect. But it does have some pretty cool practical uses in the real world, in my opinion. So, the photoelectric effect was first discovered in 1887 by Heinrich Hertz, and it is a phenomenon during which electrons are ejected from the surface of metals when hit by photons. This observation kind of assisted in the development of modern physics by raising questions about how light functions, as far as whether it's a particle or a wave. And this discovery later prompted that the realization that light comes in both forms of energy and particles. So, and at face value, it doesn't seem like it's too interesting of a discovery, but it does have some practical applications and has assisted in development of some technology. So here's the equation. It is E equals hv, and as said earlier, light striking metal causes this effect, but it doesn't occur when just any light hits a metal. So when determining whether or not this effect can take place, you have to, use this equation basically. So E is the minimum energy needed to eject an electron from metal. V is the frequency that is applied to that metal, and H, of course, is Planck's constant, 6.66 times 10 to the negative 34. So, as you can tell by this equation, there's a minimum frequency of light needed to eject these electrons, and with a higher frequency of light, electrons can be ejected with even like a low amount or intensity of light. And this range of frequency that you can perform the photoelectric effect with is known as the threshold frequency. And so next, here's a short video I could find that best demonstrates the photoelectric effect.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now let me show you that again. I've got a perspex rod here which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall, and that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on, and it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
So that was pretty cool, right? Yeah, I agree. That was cool. Oh, whoops. Uh, sorry. So some additional facts I found, just interesting things about the history of the effect is, as mentioned in the video, Albert Einstein was the first to explain this effect, although Heinrich Hertz discovered it. He didn't really use it to explain much, but Einstein used this discovery to prove that light came in both form of waves and particles, rather than just one or the other. Oh, whoops. And some of the real-life practical applications that I found is phone's auto brightness. So if you have that turned on your phone and it's bright outside, your phone detects that and brightens the screen so that you can see it. Or if it's dark, it lowers the screen so it doesn't hurt your eyes too much. It is found in camera lighting. So a camera will determine whether or not it needs to let in more light or block out more light just based on its surroundings and how much light there is. There is a form of X-ray called X-ray photoelectron oh no, I practiced that word and I still messed it up. Spectroscopy, photoelectron spectroscopy. That word. Um, Forgot what it does, but there's that. It's also used by motion sensors. So when an object is placed between like a sensor and a fixed light source, it detects that there is no longer a light source and goes off. So yeah, that's the end of it. Thank you for watching my presentation, and that's about it. Thank you. That's my work side.